Hello and welcome to this EE328 example problem. What I'd like to do is I'd like to use the Z transform to solve a non-relaxed system response in the time domain. And so the setup that I want to do is use the system in the block diagram here. So the output at time n is the sum of the input at time n with half the value of the output from time n minus 1. So translating that into a difference equation, we get y of n minus 1/2 y of n minus 1 equals x of n. And so the input that I'd like to solve for is a unit step, and let's say that the initial condition has a value of 10. And so what I'd like to do is I'd like to find a total response in the time domain using the Z transform. Okay, so first things first, let's try and apply the one-sided Z transform to this difference equation. Now remember, we want the one-sided Z transform because the two-sided Z transform does not include information about initial conditions. So if I take the one-sided or unilateral Z transform of both sides, then the one-sided Z transform of y of n we'll just call big Y of z. And then we're going to take the one-sided Z transform of 1/2 times the delayed version of y. So the one-sided Z transform is linear, so if I transform a half times a function, that's the same time as a half times the transform. And so the one-sided Z transform, remember, for delays gives us the Z transform delayed by 1, but then we add in the initial condition. Okay, and then to Z transform the input, we're just going to write it as big X of z. Okay, so one more time, where did all these terms come from? Well, the 1/2 came down there. The time delay manifested itself as a multiply by Z inverse and as a add the last initial condition. This is only true for unilateral or one-sided Z transforms. If you have a two-sided Z transform, you would not have this term. Okay, so now we can isolate for y of z. X of z is already on the other side, so I'll just write it here. And I have a minus 1/2 times little y of negative 1, so if I move that over, that's a plus 1/2 little y of negative 1. And then the characteristic polynomial is 1 minus 1/2 z inverse. So there's a 1 here, and minus 1/2 times z inverse is how I got that characteristic polynomial. Now I've written these as two separate fractions. You don't have to, but if you do, then what we have here is the zero state response in the Z domain, and what we have here is the zero input response in the Z domain. And so what I'm going to do is, you don't have to do this, but I'm going to solve both of these separately and then recombine them at the very end. Okay, let's do the easier one first. Let's do the ZIR. So the ZIR part of the output in the Z domain is 1/2 times 10, so let's just call that 5, over 1 minus 1/2 Z inverse. And this, with a lookup table, we can get to be 5 times the causal exponential sequence 1/2 to the n times u of n. Okay, so this is what I would call y sub ZIR in the time domain. The other term is a little trickier. I'm going to give myself a little bit more room for it. So y sub CSR in the Z domain is the Z transform of x. So I need the Z transform of a unit step on top of 1 minus 1/2 Z inverse. Now the z transform of a unit step is 1 over 1 minus z inverse, and if I divide that by 1 minus 1/2 z inverse, I get the product of these two binomials on the denominator. Okay, so you could look this up in a lookup table. I'm going to show you one way to expand it using partial fractions. So first things first is I'm going to clear all my z inverses from the bottom. So I'm going to multiply this by z squared over z squared. And that gives me z squared on top and z minus 1 times z minus 1/2 on the bottom. Okay, each of these z squareds, I'm going to put one of them on each of the factors down here. Okay, so instead of partial fractioning that, I'm going to take Professor Pilkington's advice and rather partial fraction that function divided by z. So take one of the z's from the numerator away, and I'm left with the same denominator. And this I'm going to write as a sum of two partial fractions. Now I can do this in part because this is this function is proper. Right? It has z to the 1 on top and z squared on bottom, so there's no long division required. If we had z transformed or partial fraction this one out, this is improper. And so we buy ourselves a little bit of ease here by transforming the function reduced by one order. Okay, so in this I can use actually the cover-up method. So for k1, if I multiply both sides by z minus 1, I get the following. So, and then I can evaluate that at 1. So I get 1 over 1 minus 1/2, also known as 2. Okay, so let's do k2. But to do that, I'm going to have to put this fraction back in. Okay, to get k2, I equivalently multiply both sides by z minus 1/2, and then I plug in z equals 1/2. So I get 1/2 over 1/2 minus 1, which is -1. Okay, so now we have found that the zero state response divided by z can be written as 2 over z minus 1 plus -1 over z minus 1/2. And so now what I want to do is I want to move this z back across. And then if you like, depending on what form your z lookup table is, you could either take the inverse z transform of this line, or you could recognize that this is the same as 2 over 1 minus z inverse minus 1 over 1 minus 1/2 z inverse. This is the form that my lookup table is in, so I'm going to prefer that one. And if I inverse z transform both sides, I get y sub ZSR in the time domain is twice the unit step in the time domain minus 1/2 to the n u of n. And this term gave rise to that term, and this term gave rise to this term. Okay, so the total, y total, in the time domain is the sum of the ZIR and the ZSR. The ZSR has the forced mode, all by its lonesome out there, but the ZIR has a common mode with the ZSR. Those are the characteristic modes. So let's combine that. We get a +5 and a -1, so that's a +4 times 1/2 to the n u of n. Alright, there you have it. There is the sum of the forced and characteristic modes due to both the initial condition and the forcing function. And this was implemented using the z transform to accomplish this, whereas convolution would not help us get the zero input response because convolution only maps inputs to outputs. Thanks everyone. I'll see you in class.